So
I didn't get to check one.
So, but like the real idea, no, is to kind of model how collaborative projects come about. So the way it usually works with me is I like talk with people, have coffee. In fact, I still have my coffee. And then we talk about their projects. We talk about kind of how we can like maybe infuse it with a little of the kinds of things that I do. And then we ultimately write an abstract. It gives us the idea of where we're going afterwards. And I think it could be useful certainly for new lab members, but it could also be useful for people more generally. So, and I want to make it as realistic as possible, which we did, because like I hear you have like some ideas about like how neurons do something. Tell me about it. Oh, and by the way, we have lots of like writing things here, and we have a table that we can write on.
I can't see that.
So
They will not see it. It's for us.
the gist of the project is that neurons, we know in aggregate can perform these complex functions. We know that neurons
like
individually, right, and we know that neurons individually can perform complex functions from Ilenna's work.
Ilenna's work,
Right, it's possible, but we haven't necessarily shown whether or not that is a realistic thing that neurons can even do, given whatever biological constraints that may exist. That's a limitation of that kind of work too.
Right. And one thing that we'd like to explore is, can we both empirically but also mathematically prove that you could, for example, design an algorithm and optimize it and build it out of neurons, not in a learned way, but in an actual concrete, deterministic way.
So hold on, you want like a compiler into neurons or something like that?
I would love a compiler into neurons.
Okay, so no, let me be sure that I understand it. You want something where you basically give me some computer code, like maybe Python. It implements the sorting function or something.
Right.
And you want to build something that takes as input like that meaning at that level, right? And makes a bunch of neurons that do it.
That's what I don't know if I'm representing our joint idea well.
To be honest, I have a lot of difficulty understanding what exactly compilers do, so I didn't really come from that particular angle. But if you could explain, like I mean, like I may understand compilers, but I want to be on the same page. But yeah.
So
because
we
it
have
might
like,
be what I have already in mind too. It's just I'm not quite.
but you've always done learning in a way, no? Like, so let me understand. So Ilenna's kind of shown that you can learn interesting things like face recognition or like character recognition, so she's done. But you don't want to learn it. You want like rather something that like I write it and it makes a network.
Right, and I think that there's a crossover point, right, where if what you're doing is building this out of a neuron that you've programmed genetically or physiologically or whatever to just do like a binary XOR, that's like kind of an uninteresting thing because you've just built a worse computer that needs sugar. But but like you can learn the parameterization of taking advantage of all of those really cool things that neurons do that computers don't do. So there are things like time dependence. There are things like adaptive responses that make neurons more efficient computers than like a traditional binary logic gate or Boolean logic gate. And so I think that if one goal that we put out there is let's build a compiler, I'm going to give you Python and you have to give me a set of neurons that do this thing. It's kind of uninteresting to like build them out of binary XOR gates.
It's a little bit a blast from the past for me. So back when I entered neuroscience, there was this thing where people would publish all these papers. This is how a bunch of neurons can do winner take all.
Right.
This is how a bunch of neurons can do multiplication. This is how a bunch of neurons can integrate something.
Yeah.
It was always kind of a human doing.
Yeah, one critical thing here is that like I think that if we handwrite like Fibonacci number generators in neurons, that's also kind of a failure mode, right? Like I think what's important here is to show that like it is a completely reasonable thing for a set of neurons to compute a deterministic function. And I think that it's like both like a cute thing, like, look, you can make a compiler out of neurons, that's fun. But I also think it's interesting to say there might be structures in the brain that are not learned that, you know, emerge and compute a function. And we kind of know this is true. I mean, like I think of like sound localization, which is like a network that exists in every single brain and it is the same network. Right. And then there are like certainly like invertebrate networks that are deterministic that just like show up, but they do a function, and the parameter space of possible things that set of neurons can do is constrained.
That's interesting. So like when you come at it like when you bring up sound localization, which is you know, we know that can happen within dendrites through this, another way of calling it is coincidence detection, right? And we might say like approach that definition of function that a neuron might be doing from like a behavioral point of view where like, okay, this is what it is doing. It is doing coincidence detection, therefore it is useful for sound localization. My understanding of, you know, what you mean by functions like binary XORs
Mm-hmm.
is like, I would love to hear how it is of a similar class of functions as something like coincidence detection, where it's determined by its structure and everything, or is it some other kind of abstraction of function, like we feed it some input, it produces an output, therefore the function. And I think that defining that, maybe not now, but further on, might help guide us toward what exactly we're trying to figure out here.
So I think what he wants is basically a 2002 PhD student in a box that like writes papers about how neurons can do
It would make a 2022 PhD a lot easier to just have one of those laying around.
Okay, but like let's maybe go about like the level at which you're like, you say you don't want it long.
Well, no, I think you can learn things. I think that it would be a failure to say we're going to train a neural network to do this very simple function, but using, you know, PyTorch out of the box. We're going to learn, you know, with this big neural network how to do like, you know, counting or sorting or something. It's like, yeah, great. Like you just proved that neural networks work, right? I also think it's kind of uninteresting to say we are going to one-for-one replace binary XORs with a neuron that computes a close approximation of a binary XOR function, because that transfer function is like trivial and we know how to do that. And like you said, that's like a 2002 project that like, yes, it works. Like we've proven that already. And I think that there's something in the middle where there's a parameterization of the anatomy or of the local physiology of the membrane that allows you to learn within a constrained range a set of, now one, oh, sorry. Go please.
So I'm still a little unclear about like the scope at which you see it. So as you say from the past, we know how to build an AND gate, and we know how to build a NAND gate out of two neurons, and we know how to build an XOR and those things. And we totally know how to build a computer out of XORs and XNORs and all kinds of things like this. So what are we trying to? I think I'm just a little, so hold on, maybe this is where the interesting thing lies. We know that we can do it with neurons, but what if we don't ask, can we do it? But we ask kind of, can we do it like really small? Do we need we need like, what do I know, like 5 neurons per XOR or something like that. We don't want like have like a billion neurons. What Ilenna showed us is like a single neuron can kind of do most things.
Yeah.
Yes. This is where I want to come in with the dendrite flavor. So it could be that if we limit ourselves to seeing what a dendrite is capable of doing, or a branch of dendrite with potentially another single other neuron, for example, then we might be able to better characterize that possibility space of what types of functions are capable with just 2 neurons. Like, for example, it doesn't have to be, it could be just 1 neuron, but what if we just had 2? And like one of the things that came up in some of our discussions was if you draw like the architecture for a neural network that is able to do XOR, it looks kind of like this, where there's like two input neurons, you've got two hidden neurons, and then you have an output. And,
right.
and it has that, you can change the weights of here and there, different thresholds, and you get a couple different ways of doing XOR. So what if, you had a neuron, say these two are its dendritic branches, and you decided, okay, well, what if this neuron here synapses onto these two, and this neuron here synapses onto those two. It's a similar structure, but it is just three neurons doing XOR, for example.
Right.
But that's just pure architecture, given the similarities between what we know with neurons and what we think of neurons and dendritic compartments as single neurons. What I said that confusingly, the dendritic compartments can be made equivalent to individual neurons in a neural network. So yeah, so that's
I think I see a space where this becomes very meaningful. Like there is this space that is interesting but feels like last year, where you can say our program ultimately has an input, has an output. I produce lots of input-output pairs. I train one neuron with this whole dendritic tree to kind of do that, and kind of you've done that. But I think what I like about it is that it's a way of going into a really big space of things that don't solve MNIST, but that really solve complex problems.
Yeah, there's a family of tasks that are traditionally on a computer built out of logic gates are hard, right? Capital H hard, right? So there are things like graph traversals or large NP-hard challenges that suffer from this von Neumann bottleneck of I have a limited number of computing things and I have more data than I have space in that bottleneck to get to my compute. Then there's the thing that neurons are really, really good at, right? Which is not clock cycle input hidden out, right? That they can compute. Their transfer function is more interesting than you could represent with a single, with a clock cycle like that. And I think taking advantage of that is really kind of the interesting, if we're doing just simple XOR or whatever our simple function is, like you said, is a last year model, we're not taking advantage of the full parameter space of what a neuron can do.
Right. So but hold on. I think here I see a way how that can be then formulated. The way we usually solve problems, we produce an input-output data set for each input, what the output should be. If our function is sufficiently simple that we want to learn, then we don't need all that much data. As the function gets more complicated, we kind of need dramatically more data. But in your case, we have the training data. Now we have Python code that ultimately has an input and has an output. Within that code, there will be times where there's places where there's natural bottlenecks. And it will calculate some things, and then we have an intermediate result, and then we calculate some things as an intermediate result. To some level, you can have a neuron basically learn multiple levels of that.
Right.
And find lots of cool shortcuts on how to use the weights better or something. But ultimately, we can say if I have the whole input-output thing, it might be impossible to learn because there's not one neuron. But you can say we can dial in how complex we want to make it. If each neuron basically is just one binary operation and it's trivial to solve.
Right.
If a neuron is 3 layers of that, it probably can still do it. If a neuron is 700 layers of that, there's no way we could learn it. So we could kind of have as input kind of the whole compute tree from the Python program, and we could use PyTorch or something to kind of get that.
Right.
And then we can kind of say, how deep can we make it so that it's still learnable? And it could automatically do that, which would basically ask, can we solve the problem with like a relatively small number of layers of neural computation?
Right.
Would that be kind of like what you guys are looking for?
I think so. Yeah. I also think that there's, you know, if what we're doing is like taking, you know, like just slightly reducing the scale of a artificial neural network, it's like kind of uninteresting. But if you are, you know, building from scratch an extremely optimal way of doing this thing, right, that is going to be faster than running a bajillion numbers through your GPU, then I think it's an interesting thing. Not only an interesting, like, oh, look, neurons are good, and they, you know, this biological compute substrate is better at just, you know, better at things than just I can do biology things, right? They can also do math things. But I think it's also interesting from a computer science perspective, where you're showing, look, for certain, you know, a certain class of functions that I don't think probably has a name, there's a neuronal network of one or more neurons that does it better than, or more efficiently than, or for lower power than your PyTorch implementation.
So I have I think 3 points of clarification, I think. So when it comes, this kind of like this idea of taking neural networks. So like when I think of a neural network, I mean like artificial neural networks where the neurons are point neurons and things like that. That's the impression I'm getting.
No, we'd be having dendrite neurons, no?
In our model, yes.
Okay, cool.
Okay, so then we're doing dendrite models.
We're doing your kind of model.
Yes.
Jonesian neurons.
Jonesian neurons.
Yeah.
I kind of like the sound of that. So that's the first point. Because the second thing is that it kind of reminds me of the David Benyagev paper where he and the team said, okay, here's an input-output function. The input is current going into a real neuron. The output is real neuron recording how many neurons in a artificial neural network, how many layers of an artificial neural network of this particular architecture is required in order to fulfill this complex function, which is a realistic function.
And the answer is like 5 or something? 7. Okay, cool.
Of their particular architecture. And it kind of had what we were kind of talking about, reminds me of that kind of flavor. And I'm bringing that up to see if I'm understanding. Okay, and then the third thing I'm forgetting. I said 3 so that I could try to.
3 is the magic number.
Yeah. Complexity. So how do we even define function complexity in ways that is methodical, so that in principle?
Yeah, so maybe let's talk about like the compute tree that we have. Like we ultimately have like a couple of inputs to our function. And now the function does things to these. What do I know? Like here we have like different things that are being done on it. And it has like a next layer where things are done to it.
These are point neurons, or
these are variables. Those would be things that like Python has a name for.
So this is like a concrete function that you're.
Yeah, yes, this is not a concrete function that I know in my head. I'm just trying to sketch something there. And we could have something like this. There's also, of course, if-then statements, but let's for the moment like.
Well, you can unroll these something lambda calculus.
Yes, we can. Yeah. And then ultimately here, like that function gives us some kind of an object. Now, you can say there exists one way of solving that, which is how you did, Ilenna. Like you basically say, I make a list of like, let's call these X and let's call these Y, and I basically train a neuron with its dendrites, F theta of X, and basically Y hat is F theta of X. So if this is sufficiently
I was just motion because it may be difficult for people to engage with what we're talking about if they can't see.
If they can't see what we write, yes. Well, they're supposed to see how we talk, not the exact details.
Okay, cool.
I think it's super nice that you, okay, in any case, you can say, what you do is you basically take joint pairs of X and Y, basically what X is and what Y should be.
Mm-hmm.
And there's this Python code that makes it. And then you basically have a dendrite that estimates this output Y based on the inputs with lots of parameters. And if the problem is sufficiently simple, it will basically get it perfectly right, in particular because it's binary. And we can therefore like list all of them.
Mm-hmm.
Now, imagine this gets to be very, very large. Yeah. Then there's no longer any chance to solve it.
So you're saying there's no way
to solve it with the way you've been doing it.
Oh,
like,
right.
Kind of like this to be difficult function. So what I thought that you told me is that that we can now dial that. Let's call this Z, and then we can basically say, we view this as one neuron, and this is a neuron, and this is a neuron, and this is a neuron. When we basically then here solve that machine learning problem as Z had with like realistic dendrite neurons is F theta Z of X.
Right, and now you have this very condensed tree that is like easily learned.
Yeah, and then you have Y hat. That output here is basically F of theta Y of Z hat.
Yeah,
and now you can so you can basically dial in how complex that is. And the cool thing is because you have access to the Python code, you can do it arbitrarily well.
And I think that one, yes, yes, and I think that one important benefit here is that like if your function that whatever it is that takes, I don't know if it's bad or if it's just hard to see, but if you have, whatever your function is that, your like function of this that returns, like a single neuron, whatever this function is, you can either learn that like you're doing here, or you can, I think, be clever about the language that you write your compute tree in and say, this is going to be a deterministic function that looks for like, look, if I've got this shape, and this is like a plus of 2 integers, right? And then I also have this, and this is a plus, right? And these are now 3, integer 1, 2, and 3,
this
right?
Is a compute tree? This is
a compute tree, right? So I'm saying I'm gonna, this is representing the function A plus B plus C using 2 binary adds, right? I can simplify that into a single, or whatever it is. But this function now, the reason that I'm doing this is because you can say now the function here, you can say the library of things that I have to work with are anything you can put into a GPU or anything you put into a CPU. It's like optimize it, please. Or you can say the only thing that I can give you is like I can keep this organoid alive in a dish, but everything is glutamatergic, and I can only do XYZ transfer function of that neuron in this organoid, and so I want you to optimize it into those types of neurons because that way I can compute it in my petri dish. Question. I don't know. I said that as a statement, but I meant it as a question.
Yeah.
But like now you abstracted all that into this one function.
I thought I understood what you wanted to do until you just said what you said.
Well, no, I'm improvising here. I mean, I think that it's like if you abstract all of that complexity into this one function, you can swap that function out with another function that does the same thing but in a different way, right? So you say like I'm either going to simplify things like this, or I'm going to say like I am going to go to my wet lab and I'm going to print out this series of neurons. So this optimization function needs to print out neurons in an assembly that I can actually print into a dish.
Yeah, but I think that makes it one step needlessly complicated from a project perspective. Like,
well, I mean,
something that's like well doable.
Yeah, you just want to send it that says like, oh, insert F here.
But here's the difficulty. Like here's how I see the problem. We are basically choosing based on that Python program these intermediate neurons where we basically take the overall compute tree and we divide it into single like Ilenna type models.
Mm-hmm.
So we need to choose a subset of nodes that basically separates the overall compute tree into pieces.
Yes.
And it's a choice. No, I said we divide here, but we could have divided here and there and there. So
I know. So I've now, like, based off your explanation, I'm picking back up from based off of our conversation before on what fits in that spot. So any one of these could be doing some form of function depending on how it's parameterized, whether it be number of branches, number of compartments, the distribution of ion channels that exist. But what we want to know is, basically, what is the, let's assume that the basic unit of computation in the brain is a set of dendritic branches. And that would be the primary assumption that we'd be dealing with. And
right.
then
That's the primitive.
yes.
Right.
And then how do we know it's doing the computation? Well, we could, or how do we know that what we've got is capable of doing a computation? We could give a set of perhaps like harkening back to old work, logic functions or other kinds of functions that we would think are, or we assume are pretty simple, but could be used in, what's the word? Conjunction composition. It can be composed with other functions in this way. So like, for example, this 3 inputs coming together into one, like here and here, leading to a single output could be, some sort of primitive, or like one going to splitting off into 2. It's just like a kind of a merging of taking a, when I say parameterized, I mean like, you've got some like morphology, whether it be, can I have blue?
unless you're blue.
Yeah.
Here's an extra blue in case it doesn't work.
Yeah, so you could have morphology here, where you could have something that is branched into 2 or 3, but you could also have a morphology where you've got, a second neuron, for example. This is why I keep hearkening to some second neuron that allows for a kind of taking a single input and branching it out into 2 or divergent. This is a divergent kind of function. So like thinking what are the primitives here where, this could be a primitive, this could be a primitive.
This is something that I've spent a lot of time on because I think this is like you say, I'm going to build my network out of, instead of all PyTorch primitives, I'm going to build it only out of some universal gate set, whatever it is. So I'm going to build this entire thing out of XOR as an example. And then I'm going to say, I know how to build XOR out of a neuron. So in the simplest possible case where I just give up and I throw up my hands and I say, I have to simulate this really giant XOR network. It's like, great, we have like confidence that we can do that. Then you say, I know, if you arrange 10 XORs like this, that is the same as doing a integer AND operation or integer subtraction operation. And I also know how to build that out of neurons. And so I can go simplify, I'm going to take this and I'm going to go to my library and I'm going to say like, do I have that shape anywhere? It's like, oh yeah, it lines up really nicely here. I'm going to swap that out for this optimal version of that. But that way you are saying like, even if I don't know all of the optimizations that I can build in here, I can go from a version that I know I can build out of neurons to a smaller version that I also know I can build out of neurons at every step of the way.
So let me make sure I understand the algorithm. So the algorithm basically, there's 3 things. It kind of like finds the Z's, basically the places where we count. Right? Mm-hmm. It then trains units, trains pieces. It basically, the Z cut the graph into puzzle pieces. Right. So then we train the pieces, and then if we fail, then we basically return. And if success, then we basically report solution. with potentially kind of an outer loop that kind of makes that better. You can say find Z. To me, that has a bit of a graph neural network flavor.
Yeah.
We kind of want to go through that and see where we run into prompts.
And there's probably some heuristic that says like here, like this is a bottleneck because of blah, 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 the weights tend to be close to zero in this area, or tend to not be close to zero in this area, or whatever it is. Like there's maximal entropy in this part of the network, or there's minimal entropy in this part of the network.
Also, small number of lines that go through it.
Right.
Now,
What does it mean to train a piece? Like, what is
that's what you've been doing. No, like each piece here, like has a couple of inputs and it has like an output. And like this could be a piece here. A piece has a couple of inputs and it has an output, and is basically the primitive that we train to do something. And now this can be a solvable problem, in which case for all binary inputs and outputs, we get it right. Or this can be a non-solvable problem where we can't do it. If we can't do it, then basically we don't have a solution. Like if even one piece, if we cut this into lots of pieces, if even a single piece is not learnable, then we don't have a solution made out of realistic Ilenna Jones neurons.
That's now the orange here is a compute graph, PyTorch or otherwise.
Right.
But everything that you just said in this algorithm works equally well for a like traditional neural network, where instead of cutting in the compute graph space, you're cutting in the layer space.
That's right, yes.
Was that deliberate, or is that just a happy coincidence because everything is a compute graph?
It's a lucky coincidence.
But it sounds like it's a
yes, that's right. So there is a generalization of the problem, where like this could be layers. Now, so let's zoom out a little bit. Normally in this project at this point of time, I would sit down with the compiler guy, because like this is a compiler that we are writing here. We have a compiler guy sitting there, but we aren't going to do this because this is just like we just want to see like how that process works of brainstorming about the project. And we don't want a compiler guy here, but like it's possible that
that compiler guy.
It's possible what the compiler guy would say, like, yeah, we're talking about like we solved that right decades ago, and so I would like totally talk with them. But what I want to do next is now we're gonna hack an abstract to see how it would feel. Like that's like in a way like at this point of a project, I want to know if it succeeds. Will it be successful? I'm just saying we write an automatic 2002 PhD student isn't going to cut it. We need to have a better way of saying it. So let's pull up Google Docs.
Do you want to get in the Zoom call?
Yes, and I will join that Zoom call. And yes, you should also, you two can share a screen if that's fine with you.
I'm just kind of, so part of me is like understanding some parts of it. It's funny, it's like we have 3 people who understand some part of the project, but I don't think any of us understand the entirety of everything.
Welcome to my life. I never understand the entirety of the project. And that's normal, in particular early in the project. You know, like we are meeting one another. We kind of all come with knowledge and lack of knowledge in our area. So let me first join the, where's the link posted? It should be on our general chat or something.
Yeah.
General.
You have it, I can direct message.
Oh yeah, here. Zoom. Open Zoom. Join with computer audio. Hold on.
So you probably want to mute yourself and turn off the sound on your computer.
That's nice.
Great. So my God, you already have preliminary.
What? Wait.
Yeah. So it already kind of works.
Nice.
Yeah. So we can talk more about that later.
Okay, but like whatever the status of the project is, let's write an abstract.
I can do this if this is.
Yeah.
So I'll open a docs, or have you already opened one?
Yeah, I can share that with you.
We
Is
can,
that good behavior? And that way, and you can see some bullet points, but we can just use the same document.
Yeah.
are we going to start from scratch?
Yeah.
Okay.
Cool.
I sent it to your Gmail. Is that the easiest?
Send it to my Gmail. That should be good.
Is it sharing screen?
Not yet.
Oh, okay.
I'm first waiting for this.
I think there's a surprising number of bullet points in common with them.
Yeah, right.
The last time we tried to describe the whole project.
Okay, we have feedback somewhere.
You need to mute your computer and you need to turn off the sound on your computer.
I think that was just somebody else saying something.
Oh, was someone saying something? Okay.
Good. Yeah.
So if you scroll down, we have some bullet points that we can ignore. But
yeah. No. Let's imagine it was the first time. We need a title. How would we call it?
I never start with the title.
We're like optimizing. We're optimizing functions into like neural primitives.
Okay. Yeah. Neural primitives or
okay.
So
Feel free to below me.
Sure.
Write your own versions of it. I'm gonna write compiling
So
computer programs into interacting realistic neurons.
Yeah, I'm convinced. I would read that paper.
yeah, that's cool.
And
How does it say what we want to say? Then the input will be a computer program. That's cool.
Yeah.
Feel free if you want to sit here next to me. You're like,
Yeah, that's fine. I'm just kind of thinking about
I think this is right. We're taking a computer program. We're basically converting as much of it as possible into a neuron flavored thing.
and
we need some mention of dendritic
yes.
because otherwise
Yes,
people will
yes, we
think
will
they're
need the
artificial
word
neural networks.
dendritic in here.
Mark this up a little bit.
But of course, like more generally, if we succeed as that, we can later also do it with real neural networks.
Right.
But the great thing of first having this as a neural project is people will give us much less pushback.
Right. Yeah. Most definitely.
Because okay, so let's see. What's the problem? So hold on. One way of describing the problem is how people solved it before. There is a rich history of neuroscientists constructing by hand small networks that solve a given problem. That's something everyone can agree with. There's a rich history. Constructing by hand small networks that solve a given problem.
This feels to me like the target audience in this sentence is like we're saving neuroscience grad students the trouble of constructing functions by hand. But I think this is more generally like converting large, like, hey, I've got a big computer program.
I'm a
computer person.
Let's just say let's solve simple problems.
Sure.
Not like when they take, that's not like rocket science. That's not the traveling salesman's problem. That is like a simple problem. That solves simple problems. However, how to solve more complex and arguably interesting problems remains an open problem. So then our gap statement is how to solve complex problems with realistic neurons. But hold on, how to solve more complex and arguably interesting problems with realistic neurons.
Yep.
Realistic neuron remains an open problem. Okay, so hold on. Then let's structure what comes afterwards. There will be here something, what we do, and then there will be what we find, and then there will be, there will have to be a conclusion. And let's maybe first have the conclusion. So if we succeed, is that, like basically, you send me some Python code, I give you some neurons, you can print it in 3D with like biological matter or something.
Yeah.
How will it change the world?
Yeah, well, okay, so in the like go claim our Nobel Prize limit of we're going like, yeah, go print this out in neurons in a dish, you can take these computationally challenging things that are expensive to run on computer hardware, and you can run them in the same way that we abstract matrix arithmetic to a GPU, you would abstract your graph traversals to your NPU.
I want to see here, Ilenna. Yeah, like I think you have like what you want to do. I think Ilenna will be much better at seeing what our audience wants.
Right. So I feel like coming at it from having an interest in the brain, I want to understand how the brain works from this project. And I feel like when we come at it as like, here are problems, we want to solve more problems, it comes off as more of a, like, this is some implementation that is new, as opposed to, focusing on like, what do we learn about neurons this way? Or like, what exactly are we trying to find out?
So
because we're in the fuck around part, we're gonna find out like something.
But like, imagine it was successful. Like basically, you put in here's code that like maybe does maximally efficient lookups of some memory or something, right? And you have this thing that basically gives you a network that does it. How would that? Why would it impress? Would it impress you? Why would it impress you?
Well, what I would want, I would always want to go back to the brain. Is what we find, like, is what we come up with something that it is not only possible in the brain, but common enough in the brain? Like, if we find an implementation using basically wetware, can we find similarities or commonalities between the artificial wetware that we come up with what we actually find in the brain?
Because you have to impress either neuroscientists or computer scientists, but I feel like you either need to say, we learned something important about the brain from doing this, or we learned something important about the limits of what the brain could possibly do, or we learned the brain can't compute Fibonacci numbers or whatever, which is important to neuroscientists. Or you can say, like, we built a compiler out of neurons. And I think that's also interesting, but it's to neuroscientists, that's going to be like saying, like, look, we got doomed to run on a pregnancy test. It's like, that's cool, but like not a neuroscience answer.
That is an interesting example.
I
don't think it should be part of like, the abstract.
Paper two. Yeah.
And you can keep holding this. I won't.
But like, I think we're unclear what the audience is. Like, if the audience are engineers, a bit like you, then like we have this weird compiler that compiles into like the weirdest primitives you can think of.
Right. In order for it to be, I mean, it's definitely interesting, but in order for it to be useful, it needs to tell me, like, you've got a problem right now and I can make it better. And the problem is you hate running NP hard things on your Intel CPU, or the problem is you don't know how the brain works and we can shed light on how the brain works. But like, I don't think we can do both.
So not like
in one way.
For the brain, how the brain works, you can say, I have a mechanism, maybe actually a real neural network, or maybe something else that like solves a given problem. You can say we compile it into Ilenna neurons.
Yeah.
And then we ask, in a way, is it more similar? No? And we could use representational similarity analysis or something. But the idea would be that basically after the neuron optimization, it becomes more brain-like than it is before. It won't be brain-like, but it will be more.
You're saying this is for the neuroscience audiences that we can. Yeah.
How do we, so that is cool. So it's like, are we becoming more brain-like or not? And one way to think about it is like, okay, well, like, is there a certain implementation, maybe coming up with 2 different implementations at least and saying, okay, like a connectivity wise, for example, like given how these neurons are connected, they are connected in a graph that is something similar to what mammalian cortex is connected.
But I feel like the failure mode there is that like the brain is not connected with inputs, hidden outputs. Like no part of the brain does. I mean, maybe you could arguably say like you have sensory neurons and motor neurons, and that is like actuators and sensors. But like, I don't think that to a neuroscience audience, converting Python into neurons is going to tell them like, we can learn something about how the brain does this, unless we can say in places where the brain does numerical addition or whatever, we believe that this circuit is more representative of numerical addition in neurons than your like point neuron model, which I think is like totally valid because there's an enormous amount of literature on like, we built a computer vision system out of a neural network and thus we have simulated the brain, which.
So I feel there's 2 competing projects in the same abstract here, therefore we shouldn't go there. So one of them, so basically if we want to go the brain, but like really like we use this to understand something about brains.
Yeah.
Then there's really what I'd want to compile is not like Python code with a compute tree. It would be like something that we already feels kind of like brain-like, like a neural network using object recognition that they use to describe MRI data or something. So I feel we have to kind of choose between 2 projects. One of them is like basically, look, we can compile this Python thing into realistic neurons, and that is kind of cool because it gives us a way how it could work. And therefore it could maybe help us understand which functions are easily or hard, but like it's going to be in a different space than like the comparable to brain thing. I think for writing this abstract right now, I think I'd focus onto the compile into realistic neurons thing, knowing full well that we'll leave like Ilenna like less than happy.
I also think that like there is a lot of space there, and I don't know, like, are we learning anything fundamental about the brain from doing this that you couldn't learn from just thinking really hard about what a biological neuron looks like, or running Jonesian neurons in the simulator and saying like, what do they do? Because like as a neuroscientist, I would want to see like something that tells me now I know more about the brain, and I feel like we would just know more about Python code. Alternatively, you could say I'm a computer person and I have this algorithm, neural net, whatever, and it takes a long time to run. And if I do this weird thing that has to do with biology, I guess, then now it runs faster. But I feel like the neuroscience thing is a more like impactful scientific answer.
Well, let me go ahead. Something that I brought up before was this idea of neurons are plastic. So even if you did print out a function or compile a program in a certain way, you have to consider how the plasticity of the neurons evolved. Otherwise, it will run one time and never run the same way again.
Right.
Yeah.
Just dribble a little bit of
You dribble a little bit of media on it.
Yeah. It's a good job.
So, but I think let's write the technical version of that first. If we succeed as there's basically taking a VGG or something and compiling it into Ilenna neurons can be the next project, and it would very naturally answer those. And basically the metric there would be that we expect that it describes neural brain data better.
Yeah.
Whereas for the compiler, I just wanted to be kind of efficiently compiling stuff into like realistic neurons. So I think let's run with this for this abstract, and then
What
let's
are we running with?
the engineering thing. We just input is Python thing. Output stuff is made out of realistic neurons, but we're not trying to explain brains directly.
Right, but we can get you a faster algorithm or something better, more compact, or a
Yeah, that's the idea.
Can we define the neuron? So like what is
it's
a
a cell,
Jonesian?
and it's got
What is the Jonesian neuron?
Okay, let's put that into the however sentence here. However, how to solve more complex, arguably interesting problems with realistic neurons that are made out of dendrites rates with nonlinear channels. Let me stop them wrong. And then the conclusion will have to be something like being able to convert arbitrary computer programs into systems of interacting realistic nodes. Promises to open the door for both using neurons as hardware and to solve technical problems and to understand potential logical implementations. Something like that. It's a little generic on the neuroscience side, but like but this is a very technical project. I mean, like, hey, it's a compiler. So now we just need some stuff to like. Now, what do we do?
Can I go back to that question of what the neuron is? So, like, when you guys say Jonesy neuron, is it the stuff I've already published or the stuff I'm working on? Because like the stuff that I've already published does not have time, but the stuff that I'm working on does.
Yes. So which is actually, I think, really interesting. Yeah. Like, so you can say we have more powerful primitives if we basically allow like later levels to feed back to the earlier ones. That's kind of a much bigger thing.
Yeah.
But at the same time, it's much harder to then like actually.
It depends on what your optimization function is, right? If your function is a lookup table that says I know how to convert 10 XORs into a recurrent implementation, then it's like easy.
Okay, cool. So, but I think for the moment, like we will see if we can get it running with your new stuff. Awesome. If we have to get it running on the older stuff, that's totally cool.
Both have nonlinear channels.
It's nonlinear, it's hierarchical, it's tree structured. I think there's a lot of the properties we're looking for. So let's now sketch the algorithm. Here we developed an algorithm. That we said we want to select the Z's and then we want to train the neurons. An algorithm that alternates between choosing which variables of the an input computer program will be represented by neurons, neural outputs by neural activities, output activities.
Really like microcircuits
and training neurons to actually implement the component. Let's put a generic. You're all laughing. What's wrong?
I'm typing and nothing's happening. Okay, that's fine.
So it alternates between those two. We will use what will we use, like checks, correctness checks. We will use.
I don't have to. I think if you can prove that each subcomponent does the same function, because we're not learning necessarily. We're not learning at this replacement stage, right? So I don't think you need to prove that you are consistent as long as you know that the input function and your transfer function do the same thing.
Right. Okay, so but now we have like
but in the learning stage you can run that verification.
Yes. Okay, but we now say we choose and then we learn and then it alternates between them until it correctly implements the overall function. Okay, now comes the
I have another question. So with regards to the neurons that are implemented, that we're going to be replacing various parts of this compute graph with, the neurons that I made are binary, are completely binary.
Right.
And so like is when you have a graph, like a compute graph, it produces, real numbers.
We'll be using a binary computer graph.
Alternatively, you do the same thing that computers do, and you just represent your floating point numbers with more neurons, and your resolution increases as a function of neurons.
Yeah, but that's gonna be a hard function.
No, I don't think so, because your lookup table just gets bigger.
But we could generalize what you did with your binary neurons to continuous outputs.
Yeah.
Mm-hmm.
Didn't your first version actually have continuous outputs?
Yeah, it's very easy. All you have to do is just use like this.
Yeah.
We're looking for like a Jones type 2.
Jones type 2.
Yeah.
So
in a way, it's more similar to the Podolsky setups, because it's like she used the two-layer neural network model of a neuron to do firing rates, which is a continuous value.
Cool. No, it's super helpful the way you embed that into the literature. You like throughout the discussion, you like added like the real literature. So let's see here. Under correctly implements the overall function. Where you find, okay, let's make up how good the algorithm is. Like, tell me how good it's going to be.
We run do.
P equals NP.
Okay, look, we no. Okay. We find.
So we're not being helpful.
No, you're like making my job just really hard, and we're supposed to finish.
Well, we're 97% as good as a GCC optimizer, but it takes a little less time.
Yeah, let's just not write that.
So I don't really understand, like when we make the compute graph, we're basically the types of functions that we're trying to do are of some family that I don't have in my head. I like whatever function family we're going to be dealing with is like we're going to say, oh, we do that well or not, or we do it to some degree or not.
Yeah, I guess I don't see how we would fail. Like I know we could fail. I'm saying I don't see what the type of failure would be. Like, are we failing to?
Yeah, I don't think there's a failure mode, but let me write what like the thing that makes this interesting is that basically it does better than the trivial. The neuron is just an act.
Like in this technical paper, in this like computer science facing, I feel like the metric is performance speed.
I would say that it's the number of operations that we have.
Yeah.
We find that our optimization allows considerably smaller sets of neurons as primitive than would be needed in the naive implementation where neurons logic gates. Something like that is okay. Let's read the whole thing. Let's see how it feels.
Can I read it?
Yes, please.
There's a rich history of neuroscientists constructing by hand small networks that solve simple problems. However, how to solve more complex and arguably interesting problems with realistic neurons that are made out of dendrites and algorithmic channels remains an open problem. Here we develop an algorithm that alternates between using a graph neural network, which variables of an input computer program will be represented by neural output activities, and training neurons. Oh, where did that go?
I just slightly optimized this.
And training neurons to actually implement the component functions until it correctly implements the overall function. That's a very long sentence. We find that our optimization allows considerably smaller sets of neurons as primitives than would be needed in the naive implementation where neurons simply implement logic gates. Being able to convert arbitrary computer programs into systems of interacting realistic neurons promises to open the door for both using neurons as hardware to solve technical problems and to understand potential biological implementations of interesting functions.
Yeah, it's a good starting point. feels like a doable, cool project.
Mhm.
And I think we can wrap up the session. People will have seen how we went about it. Thank you.
Nice.
Great set of ideas.
Yeah.
And,
Workshop.
cool. Well done. It was
Nice.
fun.
Yeah.
All right, I'm gonna stop recording.
So now I don't totally understand what this exercise was.